Hello everyone, and welcome back to TechAdventure. Hope you're doing great and staying sharp in your journey of software development, embedded systems, and interview preparation. In our previous videos, we explored the top 50 real-world C and C++ interview questions, the solid principles, and common design patterns. If you missed those, be sure to check them out. They lay a solid foundation for what's coming next. In our previous RTOS session, we broke down the basics. What is an RTOS? How's it different from a general OS? What are its key components? Threads versus processes, scheduling strategies, you name it. If that sounds new to you, go watch that first. White heavy checkmark today, we're going one level deeper. We're jumping into advanced RTOS concepts through real-world interview-style Q&A, just like how it happens in actual embedded interviews. We'll talk about how to choose the right RTOS, real-world examples, and some tricky questions to test your understanding. This is all about practical clarity and confident problem-solving. Ready to level up? Let's dive in.
Welcome to the Deep Dive. Today, we're really getting into the weeds on something fundamental for anyone building, well, almost any modern electronic device. We're talking about choosing the right real-time operating system, the RTOS. It sounds technical, and it is, but get this wrong.
Oh, it can sink the whole project. Absolutely.
Exactly. Dead in the water. So our mission today, we've basically distilled a mountain of real-world interview questions, the tough ones engineers face, plus some deep industry guides. We want to give you that shortcut, the inside track on why this matters so much, what really goes into the decision, and how the big players stack up. Understand the hidden trade-offs, the unexpected wins.
Yeah, it's foundational. Understanding RTOS choices isn't just like a technical checkbox. It's the absolute bedrock for reliable, high-performance embedded systems. Make a poor choice here, and you're looking at performance issues, yeah, but also integration nightmares that just burn time and money, or even serious legal trouble down the road with licensing.
Wow. Okay. So it really touches everything. Let's unpack that. We throw around the term RTOS, but what is it fundamentally? What's its day job inside a device?
Think of it like the conductor of an orchestra inside your gadget. Its main job is managing tasks, deciding what code runs when for how long. But the real key is precision, real-time precision. It handles timing down to the microsecond, makes sure different software parts synchronize correctly, manages memory. Basically, it keeps everything humming along in perfect, predictable harmony. Without it, complex systems would just be chaos. Like you said, a bad conductor, a poor RTOS choice can really mess things up.
Right. And those pitfalls you mentioned, performance bottlenecks, integration nightmares.
Yeah.
Can you give us a clearer picture? What does a bad choice feel like in a project?
Well, performance bottlenecks are obvious. The device feels slow, maybe misses critical timing. But integration nightmares, that's when, say, your fancy new communication stack just won't talk to your sensor reading module because the RTOS doesn't handle their interaction properly. It's like puzzle pieces from different boxes, they just don't fit. And the licensing issues? Oh boy.
Yeah.
You grab an open source RTOS, think it's free, but maybe its license forces you to open source your valuable code if you link them wrong. Or maybe a commercial one has clauses that kill your business model later. It's a minefield.
Okay.
And then there's scalability. Your prototype works fine, but add a few features and the whole thing just collapses. Because RTOS couldn't handle the extra load. It wasn't designed for that growth. So yeah, it's technical, sure, but it's deeply tied into project management, business strategy, everything.
Understood. Definitely strategic. So, okay, if I'm an engineer or maybe a team lead facing this choice, how do I make it systematically? What are the critical factors? We've dug through tons of material, real interview questions, guides, and boiled it down to like 9 essential questions you have to ask. This is the checklist drawn from experience.
Right. This is how you approach it methodically. Number 1, real-time requirements. This is huge. Is your system hard real-time? Meaning a deadline must be met, period. Think airbags, pacemakers. If it's late, catastrophic failure, there's zero tolerance.
Okay.
Or is it firm or soft real-time? like streaming video. Dropping a frame is bad, but not, life-threatening. There's some tolerance. For hard real-time, you need absolute predictability. We call it deterministic behavior, and very low jitter, which is just the variation in timing. Reliability is paramount.
Makes sense.
Yeah.
What's next? I mentioned the hardware itself plays a big role, especially on tiny devices.
Absolutely. Factor 2, resource constraints. RAM and flash memory. How much space does the RTOS itself take up? On a tiny microcontroller, every kilobyte counts. And CPU cycles, too, for low-power gadgets. You need something super lightweight.
So what are the typical go-tos for those constrained systems?
Usually you're looking at things like FreeRTOS, maybe ThreadX, or Zephyr built with a minimal configuration. If you've got beefy processors, multi-core monsters, then yeah, QNX or VxWorks start looking really attractive.
And you can't just run any RTOS on any processor, right? There's compatibility.
Exactly. Factor 3, processor architecture and portability. Does the RTOS actually support your specific chip? ARM Cortex-M R8 SCV? Maybe an older architecture. And think about the future. If you switch processors later, can you take the RTOS with you easily? Portability matters.
Which ones are generally good for portability?
Well, Zephyr and FreeRTOS tend to support a really wide range of architectures. That gives you flexibility. QNX and VxWorks are often more focused on higher-end, sometimes specialized CPUs.
Okay, so you've got the core RTOS running, but you need more, right? Networking, file systems.
Precisely. That's number 4. Ecosystem and middleware support. This is critical. Does the RTOS come with or easily integrate with things like TCP/IP stacks for internet, USB support, Bluetooth, maybe over-the-air update capability?
DUIs, security?
Yeah, graphical interfaces, security stacks, all that. Some RTOSs offer a very integrated package, like ThreadX, now Azure RTOS, works seamlessly with Microsoft's Azure SDK. Zephyr has a ton of built-in open-source middleware. QNX often provides pre-certified middleware for specific industries, like automotive or medical. That can save a lot of integration pain.
And speaking of medical or automotive,
Yeah.
certification is non-negotiable there.
Oh, absolutely mandatory. Factor 5, certification and safety compliance. If your device failing could harm someone, you have to meet strict standards. We're talking things like ISO 26262 for cars, IEC 62304 for medical devices, DO 178C for airplanes.
And which RTOSs play in that space?
The usual suspects are QNX, VxWorks, and a specific product called FreeRTOS. They are designed and often pre-certified for these high-stakes applications. FreeRTOS also has a safety-certified version, FreeRTOS, which is another common route, but getting that certification is a big deal.
Okay. Then there's the money and legal side, the classic open source versus paying for it.
Yep, factor 6, open source versus commercial licensing. Open source like FreeRTOS or Zephyr, usually free to use, free to modify, great for startups, prototypes, maximum flexibility.
What's the catch?
The catch can be understanding the license obligations, lack of guaranteed support, and no IP indemnity, that's legal protection, if someone claims the RTOS code infringes their patent. Commercial options like VxWorks, QNX, you pay. But you often get dedicated support, certified builds, and that IP indemnity. Regulated industries often prefer this for the assurance. Free isn't always cheaper in the long run.
Right, total cost of ownership.
Yeah.
And thinking long-term, can the RTOS grow with the product if we add features or make a pro version?
That's scalability and modularity. Factor 7. Can you easily add capabilities? Crucially, can you use only the parts of the RTOS you need? Keep the footprint small. Zephyr is really strong here, very modular using its kconfig system. FreeRTOS is naturally small and scales pretty well. VxWorks and QNX are modular too, but they start from a, let's say, larger base designed for complex systems.
And development tools. Debugging an RTOS sounds challenging.
It can be. So factor 8 is toolchain and IDE integration. Does it play nice with your preferred tools? IAR, Keel, maybe VS Code or Eclipse. Good debugging and tracing tools are essential. Seeing what tasks are running, when they switch, how much memory they use, it's vital.
Yeah, examples there.
Sure. ThreadX integrates tightly with tools like STM32CubeID or Azure Studio. QNX has its own powerful IDE called Momentix. Zephyr often uses a command line tool, West, combined with VS Code. Good tools make a huge difference.
Okay, last one. What happens when you get stuck? late at night, deadline looming.
Factor 9, community and support. Where do you turn for help? Is there a big active developer community online, like with Zephyr, backed by Linux Foundation, or FreeRTOS, backed by Amazon? Or do you need that guaranteed paid commercial support contract you get with QNX or VxWorks, where you can call someone and get an expert on the line? For critical systems, that paid support can be worth its weight in gold.
Wow, okay, 9 factors. That's a lot to juggle. So this is where it gets really interesting, right? Applying this, let's talk scenarios. How does this checklist translate into actual choices for real products?
Exactly. Let's connect the dots. Say you're building a tiny IoT sensor, super low power, minimal RAM, and flash. What jumps out?
Resource constraints, probably. Lightweight.
Right. So you're immediately thinking FreeRTOS or maybe ThreadX. Small footprint, efficient.
Okay. What about a medical device? Needs that IEC 62304 certification.
Certification is the driver. So QNX, VxWorks, FreeRTOS, those are your primary candidates because they're built and tested for that specific need.
Makes sense. Automotive gateway, ISO 26262 required.
Same logic, different standard. QNX, maybe an AUTOS ROS, which is specifically designed for automotive, or VxWorks again, safety and reliability are paramount.
What about something less critical? Like a Wi-Fi connected security camera for your home, or maybe a smart toy.
Okay, less stringent safety needs, probably needs networking, maybe a file system. Resource constraints might still matter, but maybe not as much as the tiny sensor. Here, Zephyr or FreeRTOS look really good. They've got good middleware support for networking. They're flexible, often open source, which helps with cost for consumer goods.
High performance stuff. Robotics with real-time vision processing.
Now you need serious horsepower and rock-solid timing. Determinism is key. That often points back towards VxWorks or QNX, known for handling complex, high-throughput, real-time tasks.
And finally, an edge device talking to the cloud, say Azure or AWS.
Ecosystem integration becomes a big factor. If you're heavily invested in Azure, Azure RTOS ThreadX is almost a no-brainer because of the tight integration. If you're an AWS shop, FreeRTOS has excellent hooks into AWS IoT services.
Got it. It's really about matching the RTOS's strengths to the project's biggest needs and constraints.
Precisely. No single best RTOS, only the right one for the job.
Okay, let's zoom in a bit further. You mentioned FreeRTOS and Azure RTOS, ThreadX, quite a bit for smaller systems. They're both super popular, especially with microcontrollers. But you hinted they're quite different. Let's compare them head to head. They might seem similar on the surface, but the philosophy, the features, the ecosystem, it matters, right?
And hugely. They represent different approaches. Let's break it down. First, ownership and ecosystem.
Right.
As we said, FreeRTOS is Amazon, AWS. Azure RTOS is Microsoft, Azure. That linkage influences integrations, support, sometimes even licensing.
Right, the licensing is different.
Very different. FreeRTOS uses the MIT license. Super permissive, basically do what you want, very few restrictions. Truly open source. Azure RTOS. It's free if you're deploying on compatible hardware that's licensed for Azure services. If not, it typically requires a commercial license from Microsoft. That's a big distinction.
Okay. What about the core kernel, how they actually work?
Both are preemptive, priority-based standard stuff. But ThreadX, Azure RTOS, has a feature called preemption threshold. It's a bit technical, but it can sometimes reduce unnecessary task switching and boost performance. ThreadX is also famous for incredibly fast context switches. Really, really fast, which is great for determinism. Its internal design uses an object-based model. Tasks, queues, semaphores are all objects, which some find more intuitive than FreeRTOS's more procedural API style.
Like Guy's voice.
FreeRTOS is generally smaller, maybe 6 to 10 kilobytes for the kernel. ThreadX is a bit larger, perhaps 10 to 15 kilobyte, partly because it has more features baked in.
You mentioned features. Does that make Azure RTOS easier to use day-to-day? Maybe for debugging?
For ease of use and API design, many would say yes, partly because of the tooling. Azure RTOS comes with TraceX, a built-in graphical tool that shows you exactly what the RTOS is doing in real time. It's incredibly helpful for debugging.
And FreeRTOS.
For FreeRTOS, you typically rely on third-party tools like Percepio's Tracealyzer. It's excellent, but it's an extra component, potentially extra cost. Architecturally, some developers just find the ThreadX APIs and internal structure a bit more elegant and consistent, especially when you start using the middleware.
The middleware, how does that compare? Networking, file systems, USB.
Big difference here in middleware integration. Azure RTOS offers a suite NetX, FileX, USBX, GUIX that are all designed together, tightly integrated, consistent APIs. It feels like one cohesive package.
Or as FreeRTOS.
FreeRTOS gives you more flexibility, more choice. You can use FreeRTOS's own TCP stack, or maybe LWIP, or another third-party library. Same for file systems. More choice, but potentially more integration work for you.
And certification, if I need that safety rating.
Again, different approaches for certification and safety. With FreeRTOS, the path is usually FreeRTOS, that commercially licensed pre-certified version. Azure RTOS often feels more turnkey. Microsoft offers pre-certified versions of ThreadX and its key middleware components. This can significantly cut down the time and effort needed to get your whole system certified, which is a massive advantage if safety is critical.
Okay, so summing that up, if I want maximum flexibility, maybe I'm using AWS, or I need the absolute smallest footprint.
Then FreeRTOS is probably your choice. Great for quick prototypes, very constrained devices, or if you want to mix and match middleware components freely. Cloud neutral, essentially, despite the AWS ownership.
And if I need that integrated middleware suite, top-notch built-in debugging, I'm maybe using Azure Cloud, or that safety certification is key.
Then Azure RTOS, ThreadX, looks very compelling. It offers faster development with that integrated package, the excellent ThreadX tool, seamless Azure integration, and that potentially easier path to safety certification. More batteries included.
That makes the distinction much clearer. Okay, let's put this all together. Theory is great, comparisons are useful, but let's see it in action. Take a real-world example. Something complex like a modern digital automotive dashboard. That has to use an RTOS, right? It's doing so many things at once.
Absolutely perfect example. It screams RTOS. The objective is clear. Show speed, RPM, fuel, warnings, maybe navigation hints, talk to the rest of the car via the CAN bus, respond to user input, all reliably and instantly.
And why wouldn't you just code that in a big loop, the old bare metal way?
You could try, but it would be a nightmare. Why RTOS is essential here. You have maybe a dozen critical things happening concurrently. Reading sensors, drawing graphics, parsing incoming CAN messages constantly, checking for emergency warnings, handling button presses. A bare metal loop would struggle massively with timing. How do you guarantee the brake warning shows up instantly while you're busy redrawing the speedometer? And RTOS manages all this complexity. It gives you predictable scheduling, low latency for critical events, and keeps tasks isolated so they don't interfere.
Okay, so if you were designing this dashboard with an RTOS, how would you break down the work into tasks?
You'd create an example task structure. For instance, a CAN receive task at a very high priority. It just listens for messages from the car's network, speed, engine status, warnings. A sensor processing task, also high priority, reading things like the fuel level sensor or temperature. Then a UI rendering task, maybe medium priority. It wakes up periodically, say every 50 or 100 milliseconds, reads the latest data, and updates the screen graphics smoothly. A crucial warning alerts task, top priority. If the CAN task gets a critical engine fault message or the sensor task sees overheating, this task immediately triggers a visible or audible warning. No delays allowed.
Makes sense. What else?
Maybe a lower priority user input task for handling button presses on the steering wheel or dash, and background tasks like a logger task to record data and a diagnostics task running self-checks, both at low priority.
And how does the RTOS juggle all of that? Step by step, what's the flow?
Okay, system boot and initialization. The RTOS starts, initializes hardware drivers, creates all those tasks we just listed. Then the CAN receive task runs, waiting for messages. When one arrives, it parses it, maybe puts the speed value into a shared memory location, protected by mutex. The sensor processing task runs periodically, reads the fuel sensor, converts the value, stores it somewhere accessible. The UI rendering task wakes up, reads the latest speed from shared memory, reads the fuel level, redraws the speedometer needle and fuel gauge graphic, uses techniques like double buffering so you don't see flicker. The alerts task is probably waiting on an event flag. If the sensor task detects low oil pressure, it sets the flag, waking up the alerts task instantly to display a warning. User input task checks buttons, maybe sends a message via an RTOS queue if the user changes the display setting. And the logger diagnostics tasks just run whenever the CPU has spare cycles, doing their background work without impacting the critical real-time functions.
So the secret sauce is how these tasks share information and signal each other without causing chaos.
Exactly. That's inter-task communication in the RTOS. You use tools provided by the RTOS. Queues to pass data packets, like sending parsed CAN data to the UI task. Semaphores or mutexes to control access to shared resources, like that memory location holding the current speed. Only one task can write at a time. Event groups or flags for signaling, like the sensor task, signaling the alert task, and timers provided by the RTOS for those precise periodic actions, like waking up the UI task every 100 meters. These mechanisms prevent race conditions and data corruption.
Okay, I'm sold on the RTOS for something this complex. Let's really hammer it home, though.
Yeah.
What's the core difference? Why is this demonstrably better than trying the bare metal approach?
Let's contrast it directly. RTOS advantage over bare metal. Bare metal often uses polling, constantly checking, is there a CAN message yet? Is there one now? Super inefficient. RTOS uses event-driven tasks that sleep until something actually happens. Much more efficient.
Yep.
Timing in bare metal is fragile. You rely on manual delays, which are imprecise and easily broken if you change the code. RTOS gives you precise timers, preemption, and priorities for guaranteed scheduling. A blocking delay in bare metal halts everything. If your UI update takes too long, you might miss a critical CAN message. RTOS tasks are often non-blocking or use RTOS primitives, so one task waiting doesn't stall others.
Scalability.
Bare metal system has become tangled messes quickly. Adding a new feature can break everything. RTOS encourages modularity. Adding a new task is relatively clean and isolated.
And debugging that bare metal spaghetti code.
Nightmare. Often just blinking LEDs and guesswork. With an RTOS, you have trace tools, like TraceX or Tracealyzer, and RTOS-aware debuggers that show you exactly what each task is doing, when it runs, how much CPU it uses. It's night and day for finding problems.
So for the dashboard, the RTOS isn't just nice to have, it's practically required for robustness and maintainability.
For anything reasonably complex and time-sensitive, absolutely, especially automotive, where safety and reliability are non-negotiable.
Right, and testing this, how do you verify the RTOS-based system works under pressure?
Testing and debugging with RTOS uses those RTOS-aware tools we mentioned. Debuggers from IAR, Keel, Seger let you inspect task states, queues, mutexes. Trace tools let you visualize the execution flow, measure latencies, spot timing issues, or priority inversions. You can inject faults, simulate high loads on the CAN bus, make sure the critical tasks always meet their deadlines, even under stress. It allows for much more rigorous testing than typical bare metal approaches.
Well, that automotive dashboard example really pulls it all together. Fantastic. So we've journeyed from the what's and why of RTOS through the crucial selection factors, compared key players, and seen it applied in a complex system. It really drives home that core message, doesn't it? Choosing an RTOS isn't about finding the single best one out there. It's about finding the right fit for your project, your team, your constraints.
Exactly. And, beyond the purely technical specs we covered, the performance, the footprint, the features, don't forget the other factors. How familiar is your team with this RTOS? The learning curve can be steep. Think about long-term maintainability. What about vendor support? How well does it actually integrate with the specific compiler and debugger you use every day? Sometimes those practicalities outweigh a small technical advantage.
That's a great final point. It's the whole picture. So for everyone listening, as you think about your own projects or maybe your next embedded challenge, beyond the datasheet, what non-technical factor, team skill, licensing core, community support might actually be the most critical for your success? Something to chew on. Thanks for joining us on this deep dive. We'll catch you on the next one.